Recording is rolling. Welcome to Tuesday, November 30th. One thing I do want to mention up at the top here is there's something weird going on with my gradebook and attendance. So my name changed somehow. I'm working on that behind the scenes, but uh, I can't actually access my gradebook right now, so I can't put in anything. I've had a few students tell me that their grades have actually changed, which I don't know. So sorry, working on that. Can't do anything about that right now. Uh, the midterm schedule was just released by the school yesterday, so here's the quick rundown. Last few days we'll be in school in December. If you guys want the full schedule, this is what it looks like, and this file is posted to Google Classroom, so you have access to it there. One of my former students, Cooper Baskell, maybe some of you guys know him, is in AP Capstone, and he's running the survey. Some do like palm oil, so he needs a bunch of students to take the survey. I think it only takes like a few minutes. Now, I will set you guys up with a lab at the end of class today, probably like the last 20 minutes or so. So that might be a good opportunity to break out your cell phone if you get a chance and answer some questions for me. But we're just going to do one question off the homework today and then take the rest of the time to do this rotational kinematic lab. So there's number 22 in your book. And that is, the hungry bear. Hungry bear. You guys see this bear walking on this beam that's maybe being held up by this support cable? Hungry bear that weighs so many newtons is walking out on a beam in an attempt to retrieve a basket of goodies hanging at the end of the beam. There's a basket of goodies. The beam is uniform, that just means that the mass is evenly distributed. It weighs so many newtons, it's so many meters long, and it's supported by a wire at a 60-degree angle. All right. The basket weighs so many newtons. Okay. You guys get that premise? Right. We've got some weights pulling down. You guys see this pivot point right here? Like this hinge? This is like a hinge, right? So this beam would be free to like pivot on that point, right? Except that everything's being held in place by this this cable. So you're supposed to do a few things with this. First thing says draw a force diagram for the beam, like a free body diagram. Now the forces are going to have actual locations, different places on the beam. That's different from before. See, before we got to rotation, normally just have all the forces coming out of the center mass of the object. But for something like a beam, you have like torque and rotation going on. You have different forces at different locations. When the bear is at, say, this distance from the wall, from the pivot point, find the tension of the wire supporting the beam and everything else. So tension of the wire. Right. And then part C says, if the wire can withstand a maximum tension of so many newtons, then what is the maximum distance that the bear could walk out? Does it kind of make sense as the bear is walking from left to right, that the tension of the cable is going up, 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 up? Okay, that makes sense? All right, so let's solve this thing. I'm going to do what I normally do, which is do the same question, just different numbers. I'm going to change the numbers. And then we'll solve this. It's number 22, hungry bear. Let's zoom out a little more. Okay. Okay. So we got a wall. There's this like pivot joint, think of it like a door hinge, okay? And then this beam. Okay. Now this beam has it has a mass and a weight, which is really distributed over the whole thing. But in terms of forces, it's perfectly fine to treat its weight as acting at the halfway point at its own center of mass, center of gravity, which if it's uniform, then that would also be the geometric center. Okay. So we're going to draw a force vector from there. Okay. There's also a basket of goodies. At the end. And that's going to have a weight. There's a bear. And no, you guys see there's going to be 3 downwards forces just from what I've drawn so far. So what's holding this up? Actually, one of the forces holding up happens to be at this joint location. Let's worry about that later. But also, we need some kind of support cable on the other end. Otherwise, you guys see it's just gonna rotate like a door, like yeah. So do a support cable out here, okay, and maybe that goes like off paper, but it's gonna have like some tension, some T tension. Right? Actually, that'll be one of the forces. Let me switch to red to draw all the forces, all the force vectors. Okay? So the beam has some weight. I'm going to give the beam a weight of 200 newtons, right? Which we're going to treat it as if all the weight's acting at the center mass, and that's perfectly fine mathematically. It gets you the correct answers. I'm going to give the basket of goodies a weight of 100 newtons. Supposed to be a force vector right there. I'm going to give the bear, he's a pretty big bear, a weight of 500 newtons. Okay. Right. Let's say those are known force values. Right. Now, we don't yet know what is the tension in the cable. Now, the tension in the cable has to follow the geometric alignment of the cable itself, right, that way. So there's going to be some T tension. That's one of the things we're solving for eventually. I think the part B question. Okay. You know what else there is going on too is at this pivot point, do you think that the beam is like pressing down and the pivot point's holding it back up? Right? Furthermore, if you think about components, think ahead a couple of steps. You guys know I'm going to break this tension into XY components, right? Okay. In fact, let me go ahead and do that now because we're going to eventually do that. Might be a good idea to have in your mind. Okay. Remember for AP, try to avoid drawing components. If you really have to, make sure you dash them. But if you draw solid lines, then the implication is that you're double counting. Okay. Right. So the fact that there is a Leffer component, do you think that that's going to push the beam into the wall and the wall has to push back with some force? Right? So there's a force from this joint that's kind of like supporting the beam and also pushing it back. Some angle this way. I'm going to draw those components. That's if they're individual forces, which breaks some rules that I told you for AP. Like don't draw components as forces, but I'm going to break that rule here just because to keep this image a little bit cleaner because it got lines all over the place, lots of numbers. I'll call this F sub X from the wall and F sub Y. And those are also unknowns. So we got like these, but I think about them as if they were individual forces. That's like 3 unknowns at this point, right? Okay. Now I also have to label some distances and an angle. So let's put the bear out here at, say 3 meters. I'll say the whole beam is 12 meters long. So 12 meters. And then, therefore, the center mass of the beam would be at half of that, which would be 6 meters. Okay. 6 meters. Okay, my picture is pretty close to scale, so that's probably close enough. Right? And I have to give you an angle. I'll go ahead and keep the book's angle of 60 degrees. So this will be 60 degrees. Okay? And if you like, guys, if that angle is 60 degrees, then what is this angle right here? Also 60 degrees. Good call. Right angle there. Okay. All right. So if everything's in equilibrium, I mean, if it's not moving, it would be equilibrium. Right? Equilibrium means no net force, not accelerating. Here, equilibrium. Really, I need 3 conditions for a 2-dimensional problem. Right. So I got x-axis, y-axis. Right. One condition is that the sum of the forces in the x has to be 0 newtons. Another condition is sum of the forces in the y direction has to be 0 newtons. And then the third condition is that the sum of the torque has to be 0 Newton meters. Okay? Now, if you like the right-hand rule version of torque, then this is torque about the z-axis out of the paper. So all the turning moments, all the torque has to zero out. Okay? AP, remember, doesn't really care about right-hand rule, z-axis. They would just call torque clockwise and counterclockwise. Right? Okay. So do you guys see already that these two have this component of the tension and this F sub X have to be the same magnitude? That's what this condition says. Okay. Also, I know T sub Y, maybe I should label that. I got T sub X and T sub Y. You guys do see that T sub Y plus F sub Y has to balance out with these 3 down forces. That's the second condition. Okay. But the way we're actually going to solve this is to start with torque. Right? We solved a few kind of like, in fact, this is not too far from, you guys see this meter stick hanging, a couple of spring scales, weight that can slide around. Okay? Okay. Hey, this could be it. Look at this hungry bear as he walks closer to this tension. And see this tension's going up, so we do like that. Hanging bear. All right, so let's look at. Now, I did tell you guys that technically you can sum the torque about any point, and it's going to come out to 0 newton meters. But there are some points that might be either more intuitive or actually I'd be able to solve mathematically. In this case, that's the same point. And that's this actual hinge right here, this actual pivot point. I'm going to treat this point right here as I'm going to define that as the pivot point. Not because I technically have to, although it would be probably the most intuitive to do anyway, because it's kind of like a door hinge, wants to pivot about that point anyway. Okay? But mathematically, actually, it's the best point because some of my unknown values, unknown forces, are acting right at that point. And so they don't actually cause any torque about that point themselves. Right? Kind of like if you go push on the door hinges of a door, well, that's not never going to turn the door. So I don't have to worry about the torque from this point of view. So if I'm going to start with this torque equation, and I select this as my pivot point, mathematically, that's a really good choice. Because from that point of view, it looks like the bear is trying to make this turn clockwise. I'll just call it some generic torque. The beam itself has a weight that's saying, let's also go clockwise, some torque. The basket of goodies, way out here, is causing another torque. Maybe it's not as much torque because it doesn't weigh as much, but maybe it's more because there's a longer lever arm. Right? Think about sort of like that. Okay? And wow, that sure does look like a lot of clockwise torque. But this cable is holding it back in place. It's checking it with some counterclockwise torque that has to, that one needs to balance those other 3 torques. You guys see that? Okay. So let's start with the third condition, just like I said we were going to do. Okay. Some of those torques has to be 0 newton meters. Okay. And you guys ready to set up an equation? Okay. Before I move the page, any questions about anything so far? You guys got that? Okay. All right, let's set up a torque equilibrium equation. So you guys remember torque, of course, is R cross F. Okay. So let's do RF for each one of those 4 torque values. So the bear, remember, was at 3 meters and weighed 500 newtons of downforce. Okay. Plus, maybe I'll do actually, I want to give you guys good habits. Traditionally, clockwise is treated as negative torque, so maybe I'll call downforce as the negative direction. I should do that, right? Just for good practice, in case you guys see this in college. Okay? Plus, the beam itself, we're going to treat the weight as if it's acting at the center mass of the beam. Now that would be at 6 meters out, and the beam weighs 200 newtons. And I'll call that negative because I'm going to call down the negative direction, so up would be positive. Okay. Plus, the basket of goodies is out at 12 meters, and it weighs 100 newtons, so I'll call that negative 100 newtons. Okay. Then plus out here at also 12 meters, is where the cable tension is. Right? Now, is that full cable tension causing the torque, or is it only one component of it?
Is it just the upwards?
Yes, just that upwards component, exactly. And that's what this whole cross product is about, R cross F. Right? That's why I always say R cross F, because cross product is a type of multiplication between 2 vectors, right? Vector. Right? Just the perpendicular parts. So if the radial arm is horizontal, only the vertical part of the tension is actually causing any torque. That's that right there, T sub y. See, the T sub x, that's not causing any rotation, just that vertical component. Okay? So I'm going to say it's T sub y, and we're really going to solve for T sub y, is at that torque, right? This is all equal to 0 Newton meters. Put that there. Okay? You guys get that set up? Right. See, once you got that set up, okay, if you understand the picture, even better yet, if you guys can draw that picture yourself just from scratch, right? I mean, that's why I give you guys these homework problems, right? Go home and see if you can do them from scratch. And set up this equation, then we're just some algebra steps away from figuring out this component, and then we'll be really close to getting everything we want. So what's 3 by 500 plus 6 by 200 plus 12 by 100? That's right, 3,900. I'm going to take all this stuff, add it over. So I got 12 meters times our mystery t sub y, just that component of the tension, comes out to 3,900 Newton meters. Okay, divide both sides by 12 meters. I'm getting tension in the y direction is 325 newtons. Okay? Now, that's not exactly what we're interested in finding, but that is a really important middle step. Or dash outline that. Okay, is that okay so far? Okay. Okay. Hey, what if this cable was not pitched at an angle? What if it was straight vertical? That actually would be the answer, wouldn't it? Just be 325 newtons. Okay? The fact that it is at an angle means that the actual tension in this cable is going to be what? More than or less than 325? Has to be more, right? Exactly. If for no other reason, you guys can get that based on the geometry of a triangle. The longest side of a triangle is the hypotenuse. I said. Okay, so do you guys see the bigger principle then? That the more you make this cable horizontal, what's happening to the tension as you make it more and more horizontal? It's getting bigger, 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 isn't it? Because the vertical component must always be 325 newtons. And we're going to figure out the actual tension based on this and some geometry. Okay. So this vertical component, the actual tension in the 60-degree angle, do they have a sine, cosine, or tangent relationship? Sine, exactly. I can say, well, here's one way to write it. I could say sine of 60 degrees is equal to opposite t sub y divided by hypotenuse t. Okay? So that's 325 newtons divided by the actual tension that we care about, t. Okay? Do a little algebra switcheroo, cross multiply up the t, divide down sine 60. So it's 325 divided by sine 60. I'm looking at the tension in that cable is 375.3 newtons. There you go. 375.3 newtons. And look at that. I mean, that only took a few lines right there. Right? So we got a torque setup, some algebra, found a component, then went back to just some geometry, and then figure out the actual tension. All right, that good so far? All right. Questions so far? You know what I want to do? I think your book asked anyway, is what is f sub y and f sub x? Okay. Now, one way you could solve for those is you could pick a different reference point as the supposed pivot point, like this point, for example, and then some of the torque about that, and then figure it out that way. But probably the more straightforward way is to look at these equilibrium conditions, specifically the force conditions, right? You guys see this one says sum of the forces in the y has to be 0. Right? Well, if you know that this one right here is 325 newtons, guys, if that's 325, and this is 100, 200, 500 down, could you guys figure out what the difference would be to solve for f sub y? Right? Here, I write that down. So if you got the fact that the sum of the forces vertical must be 0 newtons, I'm going to say that our mystery f sub y plus t sub y, which we know to be 325 newtons, right? Minus 3 forces that are acting down, the weight of the bear, the weight of the beam,
You move the paper up.
yeah, right, and the weight of the basket of goodies must zero out. Right? So let's see, what is 500 plus 200 plus 100 minus 325? I'm looking at the vertical component of that force at the pivot point happens to be 475 newtons. Okay? Now, really, that's a component, but I think your book actually couched it that way. What is the vertical component of the force? Okay? Right. Also, I want to know, what is the horizontal component? I bet you guys can beat me to the answer for that one, because you guys do see, based on this other equilibrium condition, that these two must be balancing each other out. Can you guys do the geometry to figure out what this is? Because that would just be this, the same magnitude. Okay? So here's what I do. I'm going to say that t sub x is the same thing as t sub y times, oh, wait, never mind. Well, times tan 30, but scratch that. Maybe I'll do this. Whatever t is times cosine of 60. Right? Isn't that true? So t sub x is equal to t times cosine of 60 degrees. And since t itself was 375.3 newtons, 375.3 newtons. Does anybody happen to have memorized what is cosine of 60 degrees?
Half.
It is a half. Yeah, exactly half. That's a nice one to know. Right? So what is 375.3 times cosine 60 degrees? That works out to be 187.7 newtons. Okay? Which, because that's equivalent to f sub x, you can say f sub x is also 187.7 newtons. Is that right? Okay. Is that correct? Okay. So now that we know both of these, right, we know how much of this one is based on this condition, and we know how much to the right this one is based on some triangle geometry and also this condition, right? Could you guys put these two components together and figure out what the total force is up to the right? Guys figure that out? See if you guys can beat me to the answer. Right, now that you guys have got these, beat me to the answer. So set up some geometry here. Wall, pivot. Okay. There's an f sub x. I'll go back to dash ohm to be more proper. Of 187.7 newtons. There's an f sub y of 475 newtons. Okay. I connected those tip to tail, even though this one I actually acting out the pivot point. Tip to tail. Okay, so that you can get the total force from the pivot point that's holding up, mostly up and a little bit to the right. Okay. What is the total F from the pivot point? Okay. You guys are going to use what theorem to get that? Pythagorean. Yeah, so force is square root of 475 squared plus 187.7 squared, that many newtons. Okay. 475 squared. Squared. Okay, I'm looking at basically this many newtons. Okay. Furthermore, what is this angle? How could you guys get that angle? Here's one way to get it. Inverse tan of whatever what. Yep, 475 over 187.7 newtons. Okay. What is inverse tan of 475 on 187.7? Okay. I'm looking at 68.4 degrees above horizontal. Okay. Something like that. All right. Guys good so far? All right, there was one last question. Before I get to that, let's recap what we got so far. Okay. If the bear is here and weighs this much, beam weighs this much, goodies weigh that much, and you have these locations marked out, right, then if you take sum of torque is 0, you can solve for t sub y initially, and then do some geometry and solve for the tension. Okay. You can also apply these other conditions and solve for the force components from that pivot point at the wall, and then put it all together and figure out the total force and the angle. Okay. That's all able to be determined. Okay. But the last question, we're going to change the bear's set location from 3 meters on my notes to x, some variable number, because this bear is now walking towards those goodies, wants those goodies. Now, as the bear is walking towards those goodies, what's happening to the tension? It's going up, isn't it? Right? And suppose we have a maximum tension. We know that tension can go up to, let's say it can go up to, what is it right now? It said, I forgot. It's at 375. Let's say it can go up to 500 newtons, right? Once it goes to 500 newtons, that's the breaking point. Anything beyond that, it's going to bust. You can go up to 500, right? How far out can the bear walk before that thing's going to break? Right? You guys get that premise? Right? So let's just change one thing. This 3 meters, I'm going to change it to x, and we're going to solve for x. Okay, you guys ready to solve for x? For, let's say T max is equal to 500 newtons. Okay, you can go up to 500 newtons. It's going to break. Okay, all right. So I remember we saw this with torque before. So, let's do it again. Torque. Okay. But I remember it was really the vertical component of the tension, T sub y, right? So let's figure out what T sub y max is, and that's 500 newtons times what?
960.
Yep, sine 60. So Ty max is 500 newtons times sine of 60 degrees. What is 500 sine 60? That can go up to 433.0 newtons. Okay? And so that's probably a really useful number for the torque equations, right? The vertical component of the total tension can go up to 433 newtons. Okay? Okay? Guys hold on to that number? All right, now let's go back and set up a torque equation that looks really similar to the one we just did. We're just going to change a couple of things. So we're back to our old torque is equal to R cross F. Okay? And we've got 4 torques we're going to consider. Now the bear is going to be at some mystery distance x. That's what we're solving for. What is x? So at x will be the radial arm from the pivot point. Times the weight of the bear is still 500 newtons. Plus, actually I should call it negative 500. That's what I was calling down negative. Okay? Still at the center of mass of the beam, 6 meters, is the weight of the beam is 200, and I'll call it negative 200 newtons. Okay. Plus, basket of goodies is out at 12 meters, weighs, so negative 100 newtons. Right? Plus, right, then also at 12 meters is the cable. Okay? I'm just going to put in the y component, and we've already figured out that can go up to 433 newtons, because then that's what would make the total tension go up to 500, and that's the maximum. So I'm going to put in 433 newtons, okay? And it's positive because it's acting upward, okay? Trying to cause a counterclockwise torque. Now that all has to zero out, 0 newton meters. Okay. 4 torques, 3 clockwise, 1 counterclockwise. Okay. Can you guys solve for x based on that? I bet you guys can beat me to that one. It is 6 by 200 plus 12 by 100 plus 12 by 433. All right. So I've got x times negative 500 newtons is equal to negative 7596 Newton meters. Okay. Divide both sides by 500 negative 500 newtons. And I'm looking at x is, oh, I must have done something wrong. What did I do wrong? Or newtons. 6 by 200 plus 12 by 100 plus 12 by 433.
Should it be negative 200 and negative other stuff?
Yeah. Yeah, you're right. Okay, that's what I messed up. Thank you. Good catch. I messed up my negative signs. So 6 by 200 plus 12 by 100 minus 12 by 433. Yes, scratch this. Okay. It should be negative 2796 Newton meters. Okay. All right. Divide that by your negative 500. Yeah, this looks a lot better. Okay. 5.59 meters. Glad you guys are saving me here. Okay, so that's how far out the bear can walk. About 5.5 meters. Like if the bear walks out 6 meters, well, that's too far. The tension's going to go up too much, and that cable's going to break. Guess that with the bear and basket of goodies. Right, giant torque problem. All right, let's go to some rotational kinematics. So for the rest of the class, gonna do this lab. Now, I'll walk you guys through this lab, exactly what I'm looking for. This is not gonna be AP style write-up and anything like that. I really just want you guys to get your hands on the turntable and do some rotational kinematics, just see how the numbers play out. So you guys are gonna get a turntable. Pick a reference point. It could be a point on the edge is fine. It could be a point like this right here. And first thing I want you guys to do is to measure what is the radial distance to that point. Now my point is 12 centimeters out. You guys see 12 centimeters? So I would record that number right here, 12 centimeters. Okay. Then this is going to be like a two-part story. This first set of tables here says 3 revolutions at constant angular velocity. So here's what that looks like. 1, 2, 3. I mean, you guys could do that, right? Hey, 6 pi radians. I know that 2 pi radians is 1 revolution. So 6 pi radians, isn't that 3 revolutions? What I just showed you guys? Can you guys time that? How many seconds that would take? And could you guys do this angular displacement divided by that time to get the angular velocity in radians per second? You guys can do that, right? Okay. Then over here are some linear values, like how far did this point move during those 3 rotations? And for that, you guys can reference those posters on the wall. So I've got them right here. To go from rotational stuff to linear stuff, can't you just multiply by r? You guys remember that? Okay. And same story here. If you know how fast it's spinning, can you just multiply that by r to get like linear speed and say centimeters per second? Kind of like if you point a radar gun at this dot, like how fast is it moving? Would that show up? Okay. Is that okay so far? Right, so that's the first half of the story. The second half of the story is it says release and allow to slow to stop. So I really want to show you half of it. Let me go back to do the full thing. So 1 rev, 2 rev, 3 rev, and then let it go. And just let it naturally come to a stop because there's some frictional torque. Okay? All right, so what is theta to come to a stop? Like how far did it turn to come to a stop? In radians. Now this box right here is probably the most difficult number to get. It might be more intuitive to measure maybe how many rotations does it make, or how many degrees, and then convert. So just to recap, guys, let's say it turns around like 2 times, then it comes to a stop. 2 revolutions. How would you convert that to radians? How many radians per revolution? 2 pi. Yeah, so just multiply by 2 pi. Right? Or if you counted degrees, there are 3. 1 revolution is same thing as 360 degrees, same thing as 2 pi radian. Bet you guys can figure this out, right? Okay. Can you guys? Here, let's do this first. Can you guys time that? Right. How many seconds to come to a stop? Right. And then to come to a stop, omega final would just be 0. So I went ahead and gave you guys that number. Omega average. This is something I hardly ever talk about in this class. But isn't like average velocity displacement over time, right? So take this displacement divided by this time, you get the average velocity, which should be actually it should be half of this number is what it should be. It just not about that right now, but like if this is like 10 radians per second, this number should be 5 or pretty close to 5. Right? Thinking how the graphs work. And then angular acceleration. That's the rate that it's slowing down in radians per second squared. Do you guys think you can navigate these rotational kinematic formulas and say solve for alpha? If you know this is 0, this is whatever this was, and this is some time interval, could you guys solve for alpha? I bet you guys could, right? And then can you guys translate and figure out the linear equivalence of like the reference point? How far did it move? How fast was it moving average? And what's the tangential acceleration? That's like if it was a car, what's the value of like hitting the brakes, right? And say centimeters per second squared, right? By doing all this stuff. You guys can do that, right? Okay. And last thing is I'm going to have you guys draw some graphs on the back. Now, I do only have 1 page per group. That's all I got with my printing, but we got our classic X versus T, V versus T, A versus T, and also the rotational equivalent. So theta versus T, omega versus T, alpha versus T. Okay. I'll do one of the graphs with you guys. Show you guys what I'm looking for. So this one says omega versus T. So this would be omega in radians per second, like angular velocity, and then time taken along in seconds. Now I have marked out a time value. This says T naught right here. T naught. That's the point that, see, for the first few seconds, you're gonna spin it with your finger, and then right at that point, you let it go and just let it come to a stop. Okay. So if you kept a constant angular velocity, can you guys imagine what this graph would look like during this first segment? Constant angular velocity. Wouldn't it just go like that? Right? Is that true? Right. And then right at that time, you release it, let it slow to a stop. Now, if it slows down uniformly, it goes to 0 radians per second after a couple seconds. What's the rest of that graph going to look like? You guys figure that out? Is it going to look like that right there? Okay. Actually, if you just have that graph, in principle, you can figure out what the other 5 graphs look like. But I bet you guys can figure that out anyway. Any questions about that? Right, so everything you need, got lab tables, got turntables, got lab pages. I'll walk around and help you guys out. Just pop that in the grade tray before you guys take off today.